Welcome back. In this section, we're going to look at two important theorems in calculus, Rolle's theorem and the mean value theorem. To begin with, Rolle's theorem starts off with a couple little hypotheses. We've got a function that's continuous and also differentiable, and we also happen to have at the endpoints of our interval that our function has the same y value. So we've got a function that's a nice function, continuous from a to b, including the endpoints, differentiable over that open interval, and we've also got the y values the same at the ends of that open interval, at the end of that interval from a to b. Rolle's theorem tells us then there's guaranteed we're going to have at least one value inside that interval where the derivative is going to be equal to 0. I'm going to carry out a slightly different proof here than the one that's in the textbook. And I think the one that's in the textbook is nice, but it's also nice to have a proof that maybe relies on theorems we've already discussed. And I'm going to point out some nice things in this proof that give us some ideas as to why we might care a little bit about Rolle's theorem. So first off, we'll begin with thinking about the start of our proof, beginning with taking on the hypotheses. We're assuming that we've got the continuous function, that it's differentiable. We happen to have the y values the same at a and also at b, so all of our hypotheses are met. And our goal, we need to show there has to be at least one c in that interval where the derivative is 0 at x equals c. Now, we can start to rely on some older theorems here. The extreme value theorem definitely applies, and it applies because f is continuous on that closed interval from a to b. So, hooray for us, extreme value theorem applies, which tells us we've got an absolute max and an absolute minimum somewhere in that interval. Maybe at the endpoints, maybe not, but somewhere between a and b, including a, including b, there's going to be an absolute maximum and also an absolute minimum. So now what do? Well, we think about what are the possible options for where these max and min could be. Possible, it could be that the max and min are at the endpoints. One of them is the maximum value location and one of them is the minimum value location in whatever order. And if that's not the case, then either you'll be able to find the maximum somewhere not at one of those endpoints, or maybe you'll be able to find the minimum somewhere not at one of those endpoints. Or, of course, the other possibility is maybe the maximum and the minimum, both of them are not at the endpoints. But that's kind of covered by the other two cases already. So really, we only have to look at these three options. What if the max and min are both at the endpoints? What if the minimum's not at an endpoint? What if the maximum is not at an endpoint? And if we can show in all three cases we've got a place where f prime is equal to 0, then we've done our proof. So now let's think about the first case. You've got a maximum and a minimum happening both at the endpoints. So big conclusion that we'd get there is we already knew that f of a and f of b are equal to each other, but f of c would also be equal to f of a and f of b for every c inside that interval. In other words, we would have to have a constant function. And that kind of makes sense because if you imagine a graph, and let's say I've hidden most of the graph from you, but I told you at A the y value was 5 and that was the biggest y value, and if I told you at B the y value was also 5 and that was the smallest y value, then the only possibility would be that between A and B all the y values are 5, because if that weren't the case, if you had a y value that was bigger than 5, then you'd have something bigger than the maximum, and that's not possible. Or if you had somewhere between A and B something smaller than 5, then you'd have something that's smaller than the minimum, which is, again, not possible. So if A and B had the same y value, then all the points in between would have to have the same y value, if that y value was the max and also the minimum at the same time. So that's my little explanation there. Otherwise, f of c would either be larger or smaller, larger than the max or smaller than the min, which is not possible, so you've got a constant function. And then that's really easy for you now, because if f is a constant function, then the derivative is always going to be 0. So yes, not only is there one c inside that interval where the derivative is 0, but as it would turn out, every point inside that interval would have a derivative of 0. So that's kind of the easy case. Let's look at the one that's a little bit more challenging. What if what if the maximum is not at the endpoint? So case 2, what if the maximum is not at one of the endpoints? So in other words, the maximum has to be somewhere inside of our interval. Just for convenience, I'm going to say x equals c is where that maximum happens to be. So you've got a maximum somewhere inside of our interval, and it's going to say it's happening at c. Now, here's where we start to rely on old stuff. If you've got a maximum inside of an open interval, then that is a relative maximum by definition. And what we know is then we've got a relative maximum at c. And here's where I bring back an old theorem. This is from the previous section. If f has a relative extremum, so a relative max or a relative minimum at c, then c is a critical number. So now we can say, good for us, if the maximum is inside of our interval, it has to be a relative maximum, which means at c we have a critical number. And of course, you know critical numbers happen in one of two places. Or happen for one of two reasons rather. Either the derivative is equal to 0 or the derivative is undefined. But then we think back to the very beginning of things. We suppose that f was a differentiable function. In other words, the derivative is not undefined. So good for us then, f prime of c exists, and since it exists, it must be equal to 0 then. There were only two options for our relative max. Either the derivative was 0 or the derivative was undefined. We said the derivative wasn't undefined because we know the function's differentiable, so therefore we conclude the derivative must be 0. And then for the third case, it's pretty much the same as the second. So actually, I can go a little faster this time. I don't have to really remember old things quite as much as I did here. Same sort of idea. If you had the minimum not at an endpoint, then the minimum's inside of our interval. We'll say c is where that minimum is. Same thing as before, f of c would be a relative minimum then, and c would therefore be a critical number. And for the same reasons as before, since the function is differentiable at c, then we know that c is a critical number would mean that f prime of c would have to be 0. So in all three of our cases, whether the max and min were at the endpoints, or the max was somewhere in the middle, or the min was somewhere in the middle, in all three of those cases, we were able to find at least one value of c in that interval where the derivative was 0. And so that is the end of our proof. We've shown that in all cases, if f of a equals f of b and our function is continuous and differentiable, then there's going to be some place inside the interval where f prime is equal to 0. So now some commentary about the theorem, and a lot of this is going to reflect back on our proof, some things that we sort of discovered about our interval in the process of proving it. So first thing, when we say that f prime of c is equal to 0, we're talking, of course, about the slope of the tangent line at x equals c. And so in other words, we're saying at c, the tangent line has a slope of 0. And of course, when things have a slope of 0, that means that they're horizontal. So that's really what Rolle's theorem is telling us, is if you have a nice continuous and differentiable function, and if f of a and f of b are equal to each other, then somewhere in between, there's going to be a place where there's a horizontal tangent line. And of course, we kind of know where those places would be, and that's kind of given out by our proof. If we're not talking about a constant function, then where that horizontal tangent line happens is at some critical number, either one that's related to a relative maximum or a relative minimum that's inside of our interval. So what we found is, unless we've got a constant function, you're always guaranteed that if f of a and f of b are equal to each other, we're always going to have one critical number at least in our interval. And since we've got a differentiable function, that critical number happens because we've got a horizontal tangent line, not because the derivative is undefined. Now, there's a couple little consequences that we can make. So, for any time we've got a theorem, there's things that we might think about of what if we had a few extra little conditions to throw on? Could we get some better conclusions out of it? And so here's one little thing that we could say. So here we've got a function that's not a constant function. It's continuous. It's also differentiable. And if we happen to know it has two x-intercepts, one of them at A and one of them at B, well, we know that x-intercepts have the same y value. The y values would be 0. So in other words, we've got a continuous and differentiable function. We have 2 points that have the same y value, so Rolle's theorem applies, and that's telling us that since f is not a constant function, and because of what we discovered during the course of our proof, there's going to be at least one relative extremum, either a relative max or a relative min, at least one of them in between a and b. So when we have a continuous and differentiable function, if we find two x-intercepts in between there's going to be a maximum or a minimum. There's going to be a relative maximum or a relative minimum somewhere in between, at least one of them. And of course, we can go and make things easier further on ourselves by going and saying, well, let's pretend we've got some polynomial that's of degree 1. So in other words, it's not a constant function. Constant polynomials, those are ones of degree 0. So if you're degree 1, there's at least an x lying around, so you're not a constant function. And polynomials are really nicely behaved. They are continuous and differentiable everywhere, which means for a polynomial, if you find two x-intercepts, you're guaranteed that there's a relative max or a relative min at least. Possibly more, but at least one of those in between the two x-intercepts. And you could say some further things about it too. For example, if you knew that there was a graph of a function and it was a function that was a polynomial and it happened to have x-intercepts in 3 different places, you'd be guaranteed that between the first two x-intercepts there must be a maximum or a minimum, and between the next two x-intercepts there would be either a maximum or minimum at least. In other words, if you had 3 x-intercepts, you'd be guaranteed at least 2 relative extrema. And you could go and say more generally, if you had n x-intercepts, you'll have at least n minus 1 relative extrema. So if you had something that was a polynomial and it had 10 x-intercepts, then you're going to have at least 9 relative extrema. And that's all courtesy of Rolle's theorem. Okay, so let's take a look at this, and we're going to formally show for this function, f of x being x cubed minus x, that it must have at least 2 relative extrema. We're not going to find the relative extrema, but we're just going to confirm that they exist. And so first thing I know is that f is a polynomial. And because f is a polynomial, that means it's continuous on all real numbers. And it's also differentiable on all real numbers. So we have part of Rolle's theorem met for us. And now we're going to use the idea that I sort of ended the last slide with, which was that if you're a nice continuous function and we find x-intercepts, then between the x-intercepts, courtesy of Rolle's theorem, we're guaranteed at least one extreme value. At least one relative max or one relative minimum. So let's find the x-intercepts for f. So when I let f of x be equal to 0, I've got x cubed minus x equal to 0. And that factors really nicely. We can go and say it factors as x times x squared minus 1. Or x minus 1, x plus 1. So we know that we've got x-intercepts at x equals -1, 0, and +1. So now we've got everything we need to draw our conclusion. We know that Rolle's theorem applies. And the reason Rolle's theorem applies is because we have a function that's continuous, it's differentiable, and we've got some points that have the same y value, in particular those x-intercepts. And we also know that f is not a constant function. And so now we can say between any two x-intercepts, I'm guaranteed to have at least one relative extremum. So I'm going to have at least one relative extremum in the interval from -1 up to 0, and also at least one relative extremum in the interval from 0 up to 1. So there we go. We're going to have guaranteed at least two relative extremum.